effect, and kind of also possibly getting a return value from it. But a procedure is not really like a mathematical function that's mapping an input to an output. So for kind of where functional programming came from, way back around 1928, mathematicians were interested in like what an algorithm was and what you can do with an algorithm. And so a while after that, what first happened is a guy named Alonzo Church came up with his lambda calculus and said, I think that this is equivalent to an algorithm. Anything that my lambda calculus can do, any kind of algorithm would be able to do. And so what lambda calculus is you can create an anonymous function. You can apply an anonymous function that you had taken as an argument to something else that you had taken as an argument. Or you can refer to a variable that's the scope. And you kind of used that system to prove the same thing that Turing did about 2 years later. Or actually, no, Turing was 1 year later. And one of the reasons that Turing's remembered a bit more than Alonzo Church or a couple of the other systems that came out at about the same time because everybody was kind of arguing. I think this is what a function is. Or I think this is what is a computer in like a mathematical sense. Is Turing had a really good argument that anything that any kind of human computer or whatever could do, this Turing machines could do. And they all kind of, at about that time, proved all of these systems to be equivalent. So anything that you can do in the lambda calculus, you can do with the Turing machine and vice versa. And so the lambda calculus is really kind of the original functional programming language. A couple of decades later, when we actually had computers, because Turing and Alonzo Church were doing their stuff as kind of a mathematical exploration into what kinds of things can be computed, rather than as a practical. We have electronic computers, and we want to make programming languages for them. One of the first couple of compilers was this thing called Lisp. And Lisp took a lot of inspiration from the lambda calculus. It's a dynamically typed programming language, and if you actually take a look at the feature set, most modern languages are significantly closer to Lisp than they were to the original version of Fortran and the kinds of things that they can do. Like, Lisp had if statements. Fortran at that point had like a jump if this thing is not equal to that. And a couple of decades later, in 1973, we had the first statically typed functional programming language, ML. And then a couple decades after that, people had started to get interested in something called lazy functional programming, and Haskell's kind of the main lazy functional programming language that people use. F# is a functional programming language based off of ML that's made by Microsoft, and it works nicely with C# and kind of the rest of their .NET framework. Around the same time, a language called Scala that works nicely with Java was created, and there's a lot of multi-imperative programming languages with functional influences. Like Python has a lambda keyword, for example, which sort of thing where you can create anonymous functions pretty easily. JavaScript has an interesting history where it was kind of based off of a Lisp dialect. Scala and F# are both object functional languages, as is C#, although C# is more of taking an object-oriented language and adding some functional features to it. And Rust is a newer language that takes a lot of influence from ML, but bolts it onto more of a C and that style of procedural programming. So functional programming has kind of been around for as long as Turing machines and the procedural viewpoints of programming, or imperative, I guess you should say. And it just has some slightly different solutions to the same sorts of problems. Procedural versus functional isn't so much like a screwdriver versus a hammer as it is like Japanese woodworking versus Western woodworking, where you'll have similar tools that do similar sorts of things, or the same sorts of things. So, like in Japanese woodworking, you have a slightly different looking saw. And one of the big differences is that they mostly have pull saws. So it'll cut on the pull stroke rather than on the push stroke. They do different sorts of joints
with stuff, but you can take a Japanese saw and you can use it as a Western woodworker, and you can take a lot of Western tools and use them as a Japanese woodworker and kind of mix stuff, and you can get some value out of doing that. You can get value out of doing a purely functional approach or a purely imperative approach. So it's really just kind of having a slightly different toolbox that'll make some things a little easier, some things a little harder, and kind of getting a different perspective on stuff. So one thing that is very important as like a bit of jargon is referential transparency, which is basically equivalent to purity. So an expression is referentially transparent if it can be replaced with the value it evaluates to without actually changing any of the semantics. So what do we mean by that? So if something is referentially transparent, so if 1 + 1 is referentially transparent, in any location in your program, you could take 1 + 1 and replace it with the value 2. And do people think that in general, you can take the expression 1 + 1 and replace it with 2, ignoring like operator overloading in some languages?
Well, it depends on what's next to it, because if you've got like 1 + 1 × 3, we got the order of precedence of operators, so, or parentheses. So there's sometimes where putting a 2 in there is a singular entity, while a 1 + 1 would have two different things which could group differently with the adjacent.
I mean, ignore that issue. Assume that they're in parentheses. In general, could you replace the 1 + 1 in a parentheses with 2?
Sure. Yeah, as long as it's in parentheses, yes. I think so.
Yeah. So like 1 + 1 is referentially transparent. You could even like go through your source code and replace any occurrence of 1 + 1 with 2 in the source code. And the only thing that you'd change is that your computer would get slightly less hot because it wouldn't have to do quite as many instructions. So how about this sort of thing? where we're creating a date that's June 29th, 2019, and we're extracting the date of the month from that. Could you replace that with 29 in any place in your program?
It could be a time zone issue, where if you're evaluating the date, that date in one time zone, and your current time zone, the get day is in your current time zone. All right, I'm just trying to be really, really picky here. In general, it seems like a yes, but I'm trying to think of an edge case.
I mean, if it's a constant, then yeah, I guess.
Yeah. So like that's something that is referentially transparent, just like extracting the date out of a date time. So you could just like, yeah, that is referentially transparent. What about like assigning x to be 5?
What's the value of that? What value would you replace it with?
So in C, usually x equals 5 would return 5.
Okay, but then you don't have a value of x to be used elsewhere in your, later in your program.
Exactly. So this is something that is not referentially transparent. If it were like const x equals 5, that's referentially transparent. You're just creating a constant in the environment that's equal to 5. But if you're reassigning x to be 5, that's a statement that's like fundamentally changing the state of the program. So here we have a literal array that's 1, 2, 3, and then we're indexing into it to get the item at number 1 into it. So that would also be referentially transparent. You're just doing a pure transformation of the data there. But the one thing to be careful of is mutable array and indexing into it. That depends on when you have actually doing it, right? Like, if you were to rewrite the code to do it earlier in the code, then you might get a different answer than after somebody else has gone in and rewritten the data out from under you. And if you do it later, you'll get a different value out of there. So getting stuff out of mutable data structures is not actually referentially transparent. And so the x++ is basically the same sort of thing as x equals x plus 1, which is like that. So that's not referentially transparent. Calling a setter is going to change foo. So that's not referentially transparent. Logging is something that people often kind of ignore when they're talking about functional purity, and there's, like in Haskell, for example, which is a purely functional programming language, there's part of the standard library is debug.trace that the language treats as if it's pure, but it is kind of logging something to the console. So it's something we kind of ignore sometimes. And this here is kind of an interesting one. So we have a function sum that takes in a list and it returns the sum of every value in the list. Is this referentially transparent? Does anyone have any ideas?
So when you talk about referentially transparent, are you talking about like the elements inside that being like not accessible outside? Like
Um,
the
so you have kind of an interesting idea there, but like, I mean, obviously this plus equals here is not referentially transparent. We are kind of doing this for the sake of running the side effect of updating I, so we can return it here. But as far as anywhere else in the program is concerned, if you were to call sum on a list, that's not actually changing anything in the list. It is a brick that we have made out of impure building blocks, but we have actually made a brick that you can kind of consider to be observably pure. So you can get value out of the ideas of functional programming in something like C by mostly building functions that are pure, like this. They use non-referentially transparent things inside the function, but they don't actually expose it to anyone. And in pure functional programming languages like Haskell, you can actually write components that are like this where they use mutable memory, but you can, because it's only being done in a single-threaded way, when you actually run that computation, you get back a pure result from it, and it is entirely just an optimization that you don't really need to care about, other than the fact that it could be faster. So if you care about the speed of the thing, you might care that it has the speed that you desire, but semantically, you don't have to care. So that's kind of an important thing to keep in mind if you're not working in a functional programming language day to day, or a purely functional programming language. So we just learned like what it means to be pure or referentially transparent, but that doesn't really tell you anything about like what you want to do to generate referentially transparent code. All it tells you is what you can't do, and that's not actually terribly useful. So in order to write referentially transparent code, you want to have your data all be immutable, which is to say you can't edit it. If you have a immutable data structure and you call a method on it, you don't change that version of it. You return a new data structure with that edit applied to it. Another thing is that relying on external state is not referentially transparent, because that, like in a mathematical function, you can't say like, get the current day. You'd have a function that takes in the day as a parameter. And that's basically the trick that functional programming uses, is anything that is state is just a function parameter. And then if you want to update that state, it needs to be part of your return value. Instead of doing a lot of loops, a lot of things in functional programming, you can write it recursively, and recursion is referentially transparent. Functional programming languages essentially all have first-class functions, which make it easier to implement things in a referentially transparent way. You could have a functional programming language that doesn't have first-class functions, but most people wouldn't really want to use it. And kind of the most important thing in any sort of either if you're working in an impure functional programming language, or even if you're trying to apply some functional programming stuff in a language like C# or C or whatever, is having the core logic of whatever you're doing be functional, and then having a thin imperative shell that actually interacts with the real world. So all of your business logic is entirely pure. And with what I was saying before about functional programming being similar to like Japanese woodworking versus Western woodworking, functional programming languages tend to have slightly different building blocks that we use. So a language like Haskell or Scheme or Scala has an expression-oriented syntax rather than a statement-oriented syntax. Particularly the typed functional programming languages have, instead of objects, they have something called an algebraic data type. Functional programming languages tend not to have null, and the statically typed ones tend to use type inference because there's a lot of good type inference algorithms for the kinds of type systems that they implement. And so this is just kind of a convenience thing that is really nice to have. And this sort of thing is like a slightly different building block. It's, instead of your toolkit coming with this kind of hammer, it's coming with that kind of hammer, I guess you could say. So, yes. So this right here is a little bit of Scala code. And this is saying that we have a type called color, and the color is either black or white. And there's no other things that we need to worry about here, just the black and white. And then we might have a player that has a color. Let's say it's chess or checkers or something like that. They've got a name and an avatar. And then a functional way of doing things with a expression-oriented switch statement is saying that this immutable value, color hex, is we are getting the color out of the player and then matching on it. And if it's black, this is going to be the color 00000 for the hex color codes, or all Fs if it's white. Whereas in something like C, what you would generally see is a statement-oriented syntax. You would have to say something like this immutable value, this mutable value is null, and then let's do a switch statement where we assign this based off of which branch we are in the switch statement. And so this is some Haskell code that basically does the same sort of thing. Haskell is a purely functional programming language, so we can't actually do the statement-oriented version. Here's two slightly different versions of it. This is something called pattern matching, which Haskell has, where you can just match on what the argument is, if it's black or white, and kind of define it piecewise. Whereas you could also do a switch expression, like in the Scala, where you take the color, and if it's black, this thing is going to be this, and if it's white, it's going to be that. So that's a nice way of it gets rid of a lot of stuff like this, and you can make code a little bit shorter when you do this kind of expression-based thing. And in fact, languages like C have actually long recognized that this kind of expression-based syntax is really nice with if, which is why they have the ternary statement, which is an if expression that you'd have in Haskell or Scala, just in C with kind of a much uglier syntax that's less obvious. So with pushing the effects to the edge of your program and passing state explicitly, this right here is kind of a really simple interface that you could do in Java to represent a pure game that would be like either a sprite-based game or like a 2D vector graphic-based game. So you'd have something that says what the initial state of the game is, and then you have 3 functions. You have one that takes a state and renders it into whatever kind of image the library is using, either the vector graphic or sprite or whatever. And then you have a function that takes in whatever the user input is. So like a button press or a key press or something like that, and has all of the logic to take in the current state and then produce the next iteration of the state. And then another one that'll take in the number of milliseconds that have elapsed in the game, and then step the state for implementing like the enemy movement or like the player falling or something like that. And then you'd have a state class that has all of the state of the game. So for example, a data structure containing all of the monsters and where they are, all the items in the world and where they are, the player's inventory, their stats, their health, yada, yada, yada. And then, the rest of your program would be kind of composing together the processing the input or stepping the worlds in a nice way. But with something like this, all of the interesting bits of the game are entirely pure. And then you can have an external library that implements this, that handles all of the actual kind of updating the screen and all of the actual input stuff. And you can test that stepping the world updates the game in the way that you expect, as just like, here's the previous state, let's apply whatever part of the step world or the entire thing is, and this is what it should return to. Here, this is the state that we should get back. So you can actually do like a purely functional game this way, and there's actually, in Haskell, there's a couple of libraries that implement this sort of thing. So the next important question is, why would you bother writing functional code instead of imperative? So the thing that I just mentioned, testability is pretty important. A functional component is kind of inherently testable. Everything, the only things that it cares about are the input to it, and the only thing that it can possibly do is return some output. It's not changing any state, so you can test anything that it can possibly do, because it's not like changing bits somewhere, it's not updating the screen or anything like that. So a functional component is kind of inherently testable in a way that an imperative component is not. Another thing is because everything is pure, you get some additional benefits to the kinds of reasoning you're able to do. So you're able to do more local reasoning. You don't have to keep the entire programming in your head like you do potentially with an imperative programming, or with imperative programs, where something in a far off part of the program can set a flag or change state, and that would impact the correctness of this function here. Instead, the only thing that affects the correctness of that function is like the arguments, what's in the function, and that's basically it. Another thing is that it's really easy with functional programming to make compositional components. So, for example, there is a library in Haskell for making vector images, where you can build images out of smaller ones. So there's some combinators that say, like, take these images and lay them out next to each other. And then the resulting image would be like all of the things that you pass to it laid out next to each other. Or like, take this one and put it in this direction with respect to that one, and those sorts of things. So you can just build a vocabulary for describing components and how to combine components, and you can build stuff up from them. Whereas what'll sometimes happen in imperative programming is you'll write something where you can't quite reuse components exactly. Instead, you need to implement a new component that does what that component there does and that component over there does. And it's really nice to be able to compose things together instead of like re-implementing stuff. Another thing is that particularly typed functional programming will statically eliminate various classes of bugs. So if you don't have loops, you're not going to have a fence post error in a loop. In Haskell, it doesn't have nulls. You don't get null pointer exceptions. And the replacement that it has for nulls actually, if you avoid using one particular function that just kind of gets the thing instead of like, get it, but if it isn't there, get this other thing. You're not ever going to have a problem because you forgot to handle the fact that something could return a null. And another thing that people will talk about with algebraic data types in particular is making incorrect code not compilable, but also making invalid states unrepresentable. Kind of, you should write your data types so that way the only things that they capture are the valid states, and some of the building blocks that you have in functional programming languages, like algebraic data types, allow you to do that a lot better than the building blocks that you tend to have in imperative programming languages. Particularly, first-class functions enable you to write concise code, and also the expression-oriented syntax also helps with concision. When your code is pure, there are fewer things that can happen when you refactor it. Because when you're editing state, you have to have your program, after you refactor it, edit the state in the same exact way as it did before. Whereas with functional programming, all you need is just the same edits to happen to the state from your functions. So there's fewer places that can go wrong. And then also the kinds of type systems that you have in something like Haskell or ML. After you're done refactoring your code, it is very rare for you to have, or after your code compiles after refactoring, it is very rare for you to have added any bugs to it and to have forgotten anything. The compiler will point out essentially all of the places that you need to remember to go to and fix up. You don't have that in dynamically typed functional programming languages like Lisp, though. But you still do have some of the other stuff where if you're writing pure components, you can reason about refactoring them in a local way, and it is easier to get that logic right than with imperative programming, where you might have some non-local reasoning that you have to do. Another thing is, again, because of the restrictions that you have, you can often do various kinds of optimizations easier. You might need to do some more complex analysis in an imperative language, and in a functional one, it might always be valid. So for example, in Haskell, there's something that the language provides called a rewrite rule, where you can say, like, anytime that you call this function and then that function, you can actually rewrite that to be this other thing. So there are libraries that implement loop fusion as like something that you need to get the rewrite rules correct in terms of like capturing the kinds of things that you want, but there's a lot less analysis that has to go on there. If something is pure, you can always memorize it. You don't have to worry about, well, if I do this, then I'm not going to run the side effects that I'm interested in there. If something is pure, then when you parallelize it, you're not going to get race conditions. You can just parallelize it and aggregate the results, and it's going to be correct. And likewise with concurrent stuff, you know exactly where your complexity is, so it's a lot easier to kind of reason about your code, because the simple stuff is kind of obviously simple, and then the complex stuff you've kind of pointed out as, here there be dragons, generally. And like another thing that you can do is, with the example that I had mentioned earlier, of you can go into your code and evaluate the 1 + 1 to be 2, you can have a JavaScript optimizer, for example, that takes your JavaScript, goes through it, and evaluates all of the constant expressions. And as long as those expressions are pure, whatever they evaluate to, it's not going to have any effects. You can just kind of pre-compute stuff at compile time, and it's not going to have any effect. So with the local reasoning, so here we have a function do something that does some stuff, and then we have a immutable value foo that calls do the thing, and in particular, it frobnicates the state somehow. And then later on, we also call frobnicate state. So one thing that you might think is, I'm calling frobnicate twice. That's probably inefficient. Let me extract that into a variable up above and just call frobnicated twice. In imperative programming, you need to think about whether frobnicate is doing anything effectful, and whether calling it twice versus calling it once is going to have any semantic effect. in functional programming, because provenicate is pure, you don't even need to think that's valid. Provenicate can't do anything but return a slightly different state. And if you do it twice, it's going to return the same thing both times. Whereas, say here, it might be that it doesn't like change anything in the state, but it's reading something that got changed. So here, it's getting back one value, but there it is getting back another. And that's kind of sometimes a subtle issue that may or may not actually be correct. Say like somewhere else, concurrently in the program, someone's saying state.set whatever. So that might lead to this being incorrect, or it might be what you actually want. And there's kind of a lot of subtle reasoning that you'd have to do if it's imperative that, sometimes people do, sometimes people forget about, and it mostly works out because there wasn't a race condition there or something like that, but sometimes it bites you in the ass. And it is very freeing, generally, to be able to ignore the rest of your program and just reason about your code locally, where the only thing you need to think about is, does this implement something with the right semantics? Not, is there something else somewhere in the code that's setting a flag that is going to make this wrong? And so one kind of thing with that is at QuakeCon a few years ago, John Carmack, who was one of the guys who wrote Quake and Doom and or Wolfenstein 3D and a couple of those games, had been looking at Haskell and functional programming and noted that the functional components that he had worked on, so the things in C or C++ that just took some input and returned some output, and they were implemented in an impure way, those components didn't require all that much time later on from their maintenance programmers. They kind of just worked. Whereas the stuff that was like, you need to set a bunch of flags here and then do some other stateful setup code, that was the kind of stuff that, over the 20-year lifespan of the code base required a lot of time for maintenance programmers fixing stuff when it inevitably got broken 5 years down the line. And that programmers in general are really bad at doing the integration of the cost of doing something the simple way that is brittle versus like spending a bit more time and doing it non-brittly. And for something that is code that lives for a long time, but can be significantly larger than, you think of when you're initially writing it, because it was something that you were going to throw away and then it got spun into a larger project. That sort of thing. So one thing that I had mentioned before is there is pure functional programming. And what that means is that everything is referentially transparent in the language. You can reason about your code equationally, like you did with algebra class. So it allows kind of a very mechanical way of thinking about your programs. However, because you do eventually need to handle things like putting stuff on the screen or reading in user input or writing stuff out into the wire or something like that, there's a couple of different rhetorical tricks that the languages will play to turn those things into something that is referentially transparent. Haskell does a sort of thing where instead of actually doing the effect, it returns a value that represents the effect. And then you can compose those represented effects together. And then the main takes in something that represents the composed effect of the entire program and interprets it. Clean and a couple of languages like that have something where your functions, they can have something that will only get used once, and if you pass around a world token in that thing, you can kind of make sure that anything effectful only gets called in the program in a very single-threaded way, and then nothing in your program can observe the fact that you've changed the world. And you really don't need to worry about those too much. I really love programming in Haskell. It's a great language, but if you want to learn Haskell, learn Haskell. You don't really need to worry about the rhetorical trick that it plays there, and you can just use the functional ideas in either an impure functional programming language or a multi-paradigm language like Python, or even just applying some functional programming ideas in your your Java or C. And with impure functional programming, some things are referentially transparent, and you just need to remember what is and isn't pure. And Lisp was a impure functional programming language. So as long as there have been functional programming languages, there have been impure functional programming languages. Whereas pure functional programming, it took people a while to figure out those rhetorical tricks that allowed them to kind of pretend that everything is referentially transparent, even when you're actually writing stuff to the screen. And you'd write code like that game thing that I showed before, where all of the important logic is entirely pure, but you have an imperative shell that actually interacts with the real world. And kind of that imperative shell is the hard bit to test, but it is useful to have kind of that functional core that's easy to test and easier to reason about. So it's definitely a very useful thing to do. And then kind of the other thing that you can do is, with the example I've gone back to a few times with the Japanese versus Western woodworking, you can use the Japanese tools to do the kinds of joinery that a Western woodworker does, or you could use Western tools to do the kinds of joints and some of those sorts of things that a Western woodworker would do. And so you can use kind of functional techniques in your C# code or JavaScript code to write impure components, and you're just using them because they're more concise or more readable to you or that sort of thing. So there's kind of a wide array of things that you can do with functional programming techniques and get value out of. And so I mean, there's value in doing very strict pure functional programming. There is value in doing the impure functional programming using some imperative building blocks to build pure components, and also from building impure components out of pure building blocks. And kind of the important thing there is to kind of learn both things and use the right technique for whatever you're doing, or the technique that you enjoy the most for whatever you're doing. Because, I mean, ultimately you can implement the same kinds of things both ways. Some things will be easier with one thing than the other, is all. So that is all that I have for the presentation. So what questions do people have? Or comments or anything?
So, I guess before, can you hear me?
Yes.
Yeah, so I guess before when you said Python has the lambda keyword, was that something that they had from the beginning, or was it added with the functional libraries? Like they also have filter, map, reduce, and all those functions now.
So lambda in Python, I don't actually know which version of Python it was added in, but it's a keyword to the language itself. And I mean, there's various libraries in Python to implement some of the classical functional functions like map, filter, reduce, etc.
Right.
And I don't actually know the history there of which was added first, because you can, since functions are a first-class thing in Python, you can also just pass in a named function to those things.
Yep.
I'd have to actually research the particular history of both of those things.
I mean, you could also add Java here then, because they also have a new functional interface and
Yes,
libraries there.
it's in the last, what is it, like 5 years ago maybe they added that?
Yeah.
Yeah, it's Java 7 or 8. I don't remember which one.
Yeah, and that was a pretty big thing because the people who had created Java, a lot of them came from a functional background and used scheme and that sort of thing, and they were hesitant to kind of drag Java all the way over to the functional end of things. They wanted to kind of improve the language that C++ programmers were writing applications in.
So Scala has a lot of object-oriented parts as well, though, right?
Yes, Scala, because it's on the JVM, and you can call Scala code from Java and Java code from Scala, it is a object functional language, and definitely compromises on some of the functional stuff that you have in Haskell to make the object-oriented stuff a little bit better. But there's a lot of really good functional libraries in Scala, and you can actually do pure functional programming in Scala using a couple of libraries.
Would you say pure functional programming is kind of limiting? Like, you know, Camel has parts that are not pure functional.
So it's not so much that it's limiting as there's kind of an inherent semantic complexity to it, because you need to play some rhetorical tricks to treat interacting with the real world. So effects as something that you can reason about in a referentially transparent way.
But what about complexity? You think you can achieve the same complexity for every single application of A versus B?
Complexity as in like
Computational.
like how complex the code is?
No, computational complexity.
Oh, computational complexity. So with immutability, generally writing stuff in an immutable way, you need to write stuff in a slightly less efficient way. There's more copying going on. So usually you can keep that to like a log factor. So it's really not that major. You can also have stuff that presents a nice interface, but is doing some very complex stuff under the hood to make it more efficient. And also garbage collectors in functional languages like Haskell tend to be tuned differently because it's fairly common for you to create a lot more shortly lived garbage. So asymptotically, there is often a penalty that you end up paying to write stuff in a nice functional way. It's generally not all that large. Like if you're using a tree set as opposed to a hash set, it's, your code takes a logarithmically longer time. Everything is like big O of log n instead of big O of 1. But the benefits in reasoning are something that I enjoy. And generally you end up with a program that's at a similar speed to something that you create in a imperative language. So, if you're writing really highly optimized C, you're probably not going to write a Haskell thing that's without really banging on some optimization stuff. You're not going to write Haskell that's quite as fast, but you're also not going to write Java that's quite as fast by the same token. With some toy stuff, you can write Haskell that's faster than C with the so the example that I had mentioned with loop fusion, there's a paper about writing Haskell that's faster than C with generalized loop fusion. That's taking a really straightforward, summing stuff on a list and compiling that to some crazy thing that's evaluating the list in parallel and doing everything that you'd have to do by hand in C to optimize that kind of numeric code as a library. But it's not the kind of thing that I write day to day. I'm writing RESTful web services and doing CRUD stuff, and I don't need to have hard real-time guarantees.
I guess I could Google some of these, but then from purely algorithmic point of view, is there any any kind of algorithm that you would incur at least a polynomial penalty when trying to force it to be purely functional?
I'm not going to say no, but I'm not aware of an example of that. It's entirely, but you might, but I'm not sure.
Thanks, I'll just Google that later.
Um, the normal thing that you see is a logarithmic slowdown. Or, depending on stuff, maybe a linear slowdown if you're using lists.
That's a good time to wrap this up, actually, because we are slightly over an hour now. And we are doing this again next week, where we're going to be covering another point of functional programming. So obviously this is the first in a 4-part series. So each of them will be about an hour-ish lecture that Elliot is doing. And same time, same place. So Zoom on Thursdays, just for the next 4 weeks. If anyone has anything, let me know. Obviously, let Elliot know for any other questions, but we'll be here next week.
So one thing is it's the next 3 weeks, right? Because this is first, and there's 3 more parts.
Correct. Yep.
The classic fence post error there.
See, there you go. Why do you use functional programming?
Yes.
You know,
Thanks a
classic.
bunch, Elliot.
You're very welcome. I hope everybody enjoyed it. If you have any feedback for the subsequent weeks of like higher level, lower level, that sort of thing, like if stuff went over your head, please ask and get me to like slow down a bit and explain stuff. Or, you know, if it's really basic, mention that. But, yeah. So
Thank you.
hope everybody learned something.
Thank you so much.
Thank you.
Thank you.
Thank you.
I will see everybody next time then.
Yeah. I'll see you next week and tomorrow.
The same bat place, same
Same.
bat panel.
Yep.